We looked at routing tables a little earlier, and we'll look at them again and probably multiple times, but interpreting routing tables is, can be a pretty big deal. When we do a show IP route, does it make sense? Do the entries make sense in the table itself? So interpret routing tables, kind of a big deal when we look at those. This is the out of the book routing table. Each router keeps an IP routing table. Directly connected networks and routes learn statically and dynamically. When a router receives a packet, it compares the packet's destination IP address to the entries in the routing table, makes a match. I think we've said those already. The next hop address is learned from multiple paths. If the router has learned multiple paths to the same destination, it makes a choice as to the next hop based on various factors. The metric is going to be the big thing that makes that determination. I want to bring this little guy over here again and look at the route tables, the routing tables. We'll go to a different one here, and you can see that we have formed adjacencies, that the dynamic routing protocols have communicated with the directly connected neighbors, the IGRP, and they're all on the same autonomous system. They have to be that in order to share information. Show IP route is what we're going to see with this thing. This has got the D routes. This has all got the D routes. If we go up here and look, D is EIGRP. The codes are listed in the show IP route. L is local, C is connected. The local, if you go down here, again has a 32-bit mask, which means it is a single IP address. Would be a host address if we were someplace, on a computer, we call it a host address. But it is an IP address that's associated with the C address, the 120 over here, .0/24. So it's going to be a class C network address. 130 is variably subnetted. It says in two subnets, two masks to work on it, and I guess that it is. I'd have to go back and look and see what I did with it. We have the destination network, we have the administrative distance, we have the cost, the metric that we use via the next hop address, and this again is how long the route's been available. So this been running for an hour and 15 minutes or so. Gigabit Ethernet 00 is the interface that it goes out of to get to this next hop address. When we configure them, we can specify the next hop address with a static. We can specify the interface it goes out of, or we can specify both. But we have all of these things up here, and the asterisk here is the candidate for the default. We did the default a little earlier. This one, gateway of last resort, is not set. We don't have a default route here. So if we don't have that, gateway of last resort is not set. When it is, gateway of last resort is, and then whatever the next hop address is. And here, show IP route. So it is set to network, and the zeros represent the everything, and the S with an asterisk with a star says that S says it's a static route, and you can see that up here wherever the S is, the static route. The asterisk is a candidate for the default route. The S is a static route. Local, L local, C connected. The reason the L local, the IP address, it goes to the local interface, to the local link to get to be able to use it. So we have the different elements of it. Each protocol uses a different metric. We saw these really big, huge numbers on EIGRP. Let me get an OSPF, maybe up here, and I think my OSPF, kind of an uninteresting one, but it's still going to have routes as soon as it gets its adjacencies. IP route. The only thing that shows up now, because we're still getting into the establishing the adjacencies, and hopefully we'll get those in a minute. I think that this one is done. But we have the connected and the local. When you get ready to do the network statement, do a show IP route and without them advertised. And these are the networks that you're going to advertise. Okay, we're doing loading and OSPF. We're forming adjacencies here for these things. And these are the neighbor addresses and then the interfaces that they're on. Loading to full, loading to done. So we have those things. If I go back now and do a show IP route, we have some other information. The O, we have a different administrative distance, 110, and we have different metrics. The 65. And then we have a 35. Connected. Well, 130 here. We don't have a lot. A lot of these, the IA is an inter area. That's in a different area. The objectives for this course, for this certification, is a single area OSPF, and we'll do OSPF tomorrow, do the configurations. But different protocols are going to have different metrics, different ways they calculate the best route. What gets put into the route table is going to be the one with the best administrative distance that we've talked about that doesn't show up here. We have default routes. Static routes are going to be ones that we're going to use. What do we got? R is the route source. In this case, it's RIP, the destination network. Administrative distance, and RIP's administrative distance is 120. The metric 2, which says that it's 2 hops away. The next hop via the next hop router, the router that you're connected to, 209.165. The route timestamp, basically how long have I had that route. And then the interface, the outgoing interface that this data will use. The things that we've been looking at, the routing tables, are arranged in a hierarchical fashion. The route source, the destination network, the administrative distance, the metric, the next hop, and the interface that it goes out of. We've looked at that a couple of times. A route referencing only a next hop address and not an exit interface got to be resolved to a route with an exit interface, and the router will do that. Packet tracer is a little funny. It won't let you specify both of them. So the route source, again, one of the things that we looked at, how was the route learned by the router? When we look at those things, the table shows up in the show IP route. C connected, S static, IGRP. IGRP is a Cisco proprietary, not used anymore protocol. RIP, mobile, BGP here for the B. BGP is the only exterior routing protocol. What we're concerned with in CCNA are the interior gateway routing protocols, the ones, and not IGRP, the IGRP, but interior, we'll say interior routing protocols, inside the enterprise, not outside the enterprise. BGP is going to be used on the internet to manage those. I have two route source codes for the directly connected interfaces. The C code identifies the directly connected network, and the L code identifies the local network. And what I was going to do, and what I got distracted from, is we're talking about BGP and routes, and what can they do to us. I talked about this a little earlier, and let me get this out here. There were some internet routes that got compromised. Actually, bad routes got sent to IBM, and it took down their cloud. The outage, the IBM outage caused by bad routes. Somebody sent bad routes to them to send information to the wrong place. Route tables are a really big deal. Common codes that are used. The S, and we've looked at these. The S for static. D is EIGRP, and it's one of those, okay, why D? And part of it, people say that E was already taken, and it probably was. If you look down here, E is EGP, Exterior Gateway Protocol, which is an old one. The only exterior gateway protocol, internet protocol in use today is BGP. But D is EIGRP. The algorithm for EIGRP is going to be dual, so yeah, maybe we can make a little sense out of that. O for OSPF, using the OSPF routing protocol, and R for RIP, dynamically learned using the RIP. These are the big ones, the protocol that CCNA is concerned with now is OSPF, which is a standard. EIGRP is a Cisco proprietary, and RIP is really old. But it works. It works okay on a small network. You don't want to go very big, because remember, RIP has a hop count of 16 or 15. 16 becomes infinity with it. The administrative distance, we've referred to each protocol, each configuration method, I guess would be a way to say, of routes has a different administrative distance. Administrative distance, select the best path. Administrative distance is really how much do I trust this route. And I do want to go back to the one that I had on here earlier, and I think that we can kind of see what the administrative distance does. In this router, which is running two protocols, it's running RIP and it's running EIGRP, and it's advertising networks 100 and 120 using both protocols. 50, it's got to have both protocols, because that's the interface address. We have to activate it by advertising the network that the interface that we want to use is on. And then 14 here is only advertised in RIP. If I go to this other guy down here, and this is the only other one that is running RIP, and use the show IP route, then the only RIP is 14. Which were they? The 120 and the 130, I think, were advertised in both protocols. But because the administrative distance for EIGRP, represented by the D, is better, it's the one that gets put into the route table. Show IP. Yeah, well, so this is the only one that gets RIP. The only one that's going to get shown in the IP route. If we did a debug IP RIP, and look at it here just a second, we're going to be sending routes. It should be exchanging all of these routes, but they don't get put into the route table. Let's do get rid of it with an undebug all, that it says that it is sharing the 100 and 120. It's sharing all of these things. A metric 2 to get to these things, 14, 50, 60, 70 being advertised. But when we get to the route table, we have 50 and 60 were there. Also, they're locals here. So RIP, the 14 is the only one that is the RIP. The 120, the EIGRP, still exchanging that information. If EIGRP went down, the RIP routes would then be available to get put into the route table. But the administrative distance is going to be the first thing that the process is going to look at to see which is the lower one, which of the available routes gets to be listed in the route table. And the distance is the directly connected 0. The lower, the better. So that kind of makes sense. If it's directly connected, it's really hard to make a mistake unless we type the IP address in wrong. The static route, the IP route we put in our own route, except for the default route, is going to be an administrative distance of 1, which is going to be the second most trustworthy. External BGP, which we're really not concerned about typically on the internal networks. The administrative network is 20. The internal EIGRP is 90, Cisco proprietary. OSPF 110, RIP 120. So RIP's going to be the least trusted, and that's kind of a way to think about which is the most trusted, the more trusted. It's just a way of prioritizing which of the routing protocols do we want to use. These things: reliability of the routing protocol, reliability, trustworthy, how much do we trust it, how much do we want to use it. By reliability, using the administrative distance value when we do these things. The lower the value, the more reliable that it's going to be, and it's only significant locally. It's not going to be advertised. The routing protocols or the routes on the other router will make its own independent of what goes on. A bigger table for these things directly connected: static BGP, EIGRP, IGRP, the Cisco proprietary that's no longer in use, OSPF, ISIS, RIP, EIGRP external, and BGP internal. BGP, the Border Gateway Protocol, can be either an external protocol or an internal protocol. So it can be configured in both ways. The administrative distance with the lower value gets the higher priority. The metrics are the way that the routers determine what the cost is going to be, how much it's going to cost me to get from one location to the other. Parameters used to determine the metrics vary based on the routing protocols, all the way from RIP, which uses hop count. Not really a great one, because if we had, let's do some routers here and we'll connect them together, and this, and then we'll connect these guys. If we have a situation that these are 10 gig, 10 gig, 10 gig, and these are 56K, 56K, since RIP uses hop count, it's going to cleverly go this direction. That's one of the issues with uses hop count. It doesn't care about the speed. It doesn't care about any of the other factors that goes on. It just only cares about how many routers are between me and the destination. So that is one of the issues. RIP1 is a broadcast protocol, broadcasts its entire route table. That's why we could see that one pretty quickly. So it's going to create a lot of traffic also. EIGRP uses a number based on bandwidth and delay. Yeah, it has a number of hop counts. The bandwidth and delay are the only ones. It actually has 5 elements of its algorithm, but it only uses 2 of them, the bandwidth and delay, for the calculation. Optimal path is going to be the lowest metric, the least cost to get from one to the other. If we have multiple paths, same destination, have equal metrics, equal cost, load balancing is invoked, and we did see one of those. Equal cost, load balancing. I think this one had that, didn't it? And what it will do is use both of them. When we go down here, we have 2 routes going to the 130 network. These are 90, so we have equal administrative distance and an equal cost in the metric. So we have both of the paths in the route table. What will happen is one packet will go this way, next packet will go, so it will use both of them, and the router will make the determination of how to. So equal paths, equal cost, the paths that we can get. Balance between the 2 routes. Unequal cost load balancing can be manually configured on some protocols. Not all of them allow that. What does that mean? Is I've got that 10 gig and the 56K. Obviously, most of the traffic's going to go, and not RIP. Most of the traffic's going to go on the 10 gig, but a little bit will go across the 56K. If we had a 10 meg and a 100 meg, or a 100 meg and a gig, when we do that, we could send some of it on the 1 gig, and then most of it obviously on the 10 gig. And we configure that manually on the router, on the individual protocol. On receipt of a routing update that contains a new or a changed route to the destination, adds 1 to the metric. value specified in the update. This would be RIP. That would do it that way. If I have, let me just drag this over here so that I can. If we have RIP routers, some RIP, and we'll have them connected together, and then we'll have networks, and we'll only use really small networks. We'll say that we have network 1 here. So it goes into the route table that it is connected network 1. The RIP router sends an update to router B, and router B sends it or puts it in its route table. That's down now. In its route table, that's not what we do. C is connected. When it puts it in its route table, it's going to say RIP, and it's going to give us the metric, and the hop count's going to be 1, and it's going to be we'll say N1 for the network 1. It will then send an update, say, yeah, hey, I know how to get to network 1. So C will say, hey, it's RIP. I got it via RIP. It's 2 hops away to get to network 1. And then it will use this interface as the next hop address. It knows where the information came from. Send it on down the line to D. We get RIP, and we now have 3 hops, and then it will be going to network 1. 192.168.1.1 or whatever. The next hop address is going to be this interface, and on down the line. RIP does this every 30 seconds. So slow to converge, 30 seconds, 30 seconds, 60 seconds, 30 seconds, 90 seconds, 30 seconds, 120 seconds. It can take a long time for it to converge using the broadcast. The more sophisticated ones only do updates if there are changes. They don't broadcast everything. So the next hop, usually connected to the router. This is one of the remote next hop is one of those kind of, I think, a little odd. We point out in this thing we have the router A here, IP route 10.12.0.0, where we're going to, goes to 10.15.0.3, which is not the next hop. This guy doesn't have a clue how to get there. So we have to put now in an IP route to 10.15 to go to 255.255 to 10.11.0.2 to get there. We're configuring on this router here. He will know about this network because it's directly connected. So it'll be able to get there to the next hop address, to the 10.0, the 15.0.3, this guy right here. So this is called the next hop of a remote network can be a remote router. It's called the remote next hop, I think is the terminology, not directly connected router. You can do it, but you still got to do a route to the router that gets there. So in this one, we're going to the 10.12 network, and the 10.15.03 is our next hop. We then have to tell the system, the router A, to get to the 10.15 network, go to the 10.11, go to the adjacent device. Gateway of last resort, maybe kind of sort of we've beaten this one up already. Unroutable packets. Unroutable packets, those that can't find anything in the route table. I don't have anything in there, tell me where to go. So, okay, if that's the case, all you guys that don't have a route, come here and go to the gateway of last resort, the default gateway, to do that. If it is not default gateway, unroutable packets are going to be dropped. Uses the gateway router of last resort when it doesn't have or is not able to determine a better route. So the router can't determine a route for that network. If there is a default gateway or a router of last resort, a default route, it'll send it there. Go through the same process again to see if it can find a route for it. And we've looked at gateway of last resort set and gateway of last resort not set. The S here with the star, with the 0.0.0.0 with the subnet mask is all zeros, is going to be it. And you notice here it shows administrative distance. So when we do the default routes, that's the metric. Shows the metric of one. It really won't, I don't think, do that. The administrative distance for it, let's look at this IP route, 192.168.50.2. And now we'll look at it. It wasn't there, so I was putting the default route back in. I didn't do a copy run start. I close this thing. Show IP route. It is set, and when we go down here, administrative distance here is one static route. It'll look for a route first, and then again the static routes, the administrative distance are 1. The cost of it is going to be 0, but it will look for other routing protocols before it looks for the gateway of last resort, the static with the star attached. So it contains either the next hop IP address or the exit interface, the ultimate routes. Ultimate routes, obviously the ones that we're going to go to, we want to go to. And this is we're going to go through a number of different terminologies that will happen here. We have the static route, we have the connected routes and the RIP routes, the different routes that go on here. 5 subnets for this one, and you can look at what goes on with these things. A lot of them are variably subnetted when we do that. Route with a subnet mask less than a classful mask of a network address can be an ultimate route. Ultimate routes, and we're always looking for the subnet mask less than a classful mask of a network can be an ultimate route, but we want one that has the longest prefix in it. 172.16 is variably subnetted. This is the network route that it's going to use. We have the SuperNet route here, /16. SuperNet's when we put multiple smaller networks together. Subnetting is we take big networks and make them small networks. Supernetting, we take little bit networks and make them big networks. 192.168, this says anything that /16, anything that starts with 192.168, this is where it's going to go via the IP address and the serial interface. And then we have the default in here. The network route to go from one to the other, 5 subnets, 3 masks are available on this thing. The 172.16 0, we got 172.16 1, 2, 3, and 4 in here. A level 1 network route that is subnetted and has no exit interface or next hop address cannot be these things. The level 1 routes are going to be the parent routes, and then the level 2 routes are going to be the child routes. So level 1, 172.16, variably subnetted. We have it below, and then the level 1 parent route here, the 209. We changed we're looking at a different location. Variably subnetted into 5 subnets: 209, 165, 200. 30, we have the 32 we have the connected and then the local, and then the RIP route connected and the local. So all of those are listed here. It is the parent route. It's not where we're going to go. The level 1 route that is subnetted and has no exit interface, and these are subnetted and have no exit interface, they're not going to be the ultimate route. The subnetted ones will be the ultimate routes. Subnet of a classful network address can be an ultimate route. All of the other ones here, because they've got directly connected to gig 01, they have paths, next hop addresses down here, as well as interfaces for it to go out. And these are going to be the subnetted ones, which can be the ultimate routes. The route lookup process, and these are all kind of administrative technicalities, I guess may be kind of a word for that. The best match is level 1 ultimate route is selected and used to forward the packet. When the best match is a level 1 parent route, Then it examines the child routes. A parent route, then the child routes, the subnetted routes, to find which one it's going to use, which one would be the best route for there. If I match with the level 2 child route, the subnetted one, that subnet's used to forward the packet. If there's no match with any of the level 2 child routes, none of the subnetted routes, continue searching the level 1 supernet routes where we combine multiples together. Supernet routes, and I've done this one before, but what are we talking about there? And I'll go back to Roanoke 10.60. Everything started with 10.60. We had 10.60.10.0, 10.60.20.0, 10.60.30.0. Anyhow, we can supernet this. We can move the subnet mask because these are /24s. When we would put a route at a remote location in, we would then use a 10.60.0.0/16. This would be the supernet. We took the smaller networks, the 24-bit mask networks, and grouped them together using the subnet mask. Fewer entries in the route table when you do that, and more efficient. The other thing that it does, if we then decide to make another subnet down here, I don't have to worry about adding it in the route table at the other end, because it's going to send everything as 10.60 supernetted to that location, those locations. Supernet route, the router uses that route to forward the packet. No match with any route in the routing table, the packet gets dropped, unless we have a default route. If we have a default route, it's going to go there. Otherwise, it's going to be dropped, and we'll get an error message back, an ICMP error message that the destination network is unreachable. Populating the route table. How can we get there? Static definitions, and we did the default route. That was a static route, IP route. It's directly connected. We've seen how do you get to be that? You get to be directly connected to the router. And then discovered by a routing protocol. RIP, EIGRP, OSPF. And again, OSPF is the protocol that we're going to be concerned about here. How does it get discovered by those protocols? It gets discovered by those protocols by the routers forming adjacencies, and then the adjacent routers sharing information using the routing protocol that we would have for each of them. So we connect these guys together. They each have networks attached to them. Let's try colors here. Different networks attached to them. So this guy sends the pink networks over here. I know how to get there. Send them all to me. So the pinks go into his route table. This one then sends the other ones, the black ones, over here. They go into his routing table that he sends them there. They're using the protocols, OSPF, EIGRP, or RIP, the common language, to share that information. What you advertise is the interfaces or the networks that are directly connected. The C networks, the directly connected networks, get shared or ported, or well, shared is a better word. Advertised, maybe advertised would be an even better word. Get advertised using the routing protocol. These things use EIGRP, OSPF, or RIP, whichever they do. So this guy sends all of his directly connected. He sends all of his directly connected. Now we start building a route table. If we have another router here, this guy then shares what he has learned plus what's directly connected to him here, and this guy then now sends his directly connected routes back here, which then gets sent over here using the protocols. When everybody has all of the same information, we're going to be in convergence to then route the entire network. It is possible that the same route is discovered or entered in more than one manner, and this is where the administrative distance comes in. Same destination put into the routing table, the one that remains is determined in the following manner. this says the longest prefix. The administrative distance, which is the last one listed, is the one that should be first. And hopefully we saw that when we looked at those RIP routes and those EIGRP routes. The administrative distance, EIGRP, was better. They actually had the same prefix, had the same everything, better metric, the different protocols, the better metric determined by the protocol from a single routing protocol. The metric is going to determine it. And then the multiple routing protocols, the administrative distance. So what this is really saying, and I probably confused it, but this one, the longest prefix here, we not got the multiple routing protocols. If we have multiple routing protocols, then the administrative distance is going to be the first thing that happens, the first determination. If we have the single routing protocol, it's going to be the better metric for that. After we've gone with the longest prefix, is going to be the first thing that it looks at after administrative distance. And when we look at those things, the administrative distance will dictate which protocol, with multiple protocols, that go into the route table. Main consideration when building a routing table are administrative distance, metrics, and prefix length. The administrative distance, the trustworthiness, if it learns a destination for more than one routing protocol, administrative distances is compared and the preference is given to the routes with the lower administrative distance. Again, with the one that we looked at that had RIP and EIGRP running on the two routers, which one gets into the route table is going to be the one with the lowest administrative distance, which was EIGRP. We ran the debug and can see that the routers were exchanging RIP information. So the information was there, it just doesn't go into the route table. Would be, again, to be available, EIGRP goes down, the RIP routes would be available for it. The metrics used when we have a single routing, the best path is going to be determined. And we can see that, and we'll look at it again. If I do think that I can see this here, we might have PEIGRP topology. This one here, the 192, the 120 network, those are the same cost. One in here that had two paths, or should be one that has two paths. The triangle, they're all going to be equal paths, aren't they? Equal cost, path cost. So each of these, even with this one, to get around, we should have two paths going to this network. 50. Let's try. It says it only has one path, one successor. Guess that I didn't configure EIGRP correctly on that. Some of these things I've done and I forgot what I did to them to try to show me or to show something is misconfigured on purpose. To populate the routing table, the routing process, the protocols, we have link state protocols and distance vector protocols. Link state, the Dijkstra algorithm is going to be used in it. Link state OSPF is the one we need to know about. Distance vector RIP, and it says EIGRP. EIGRP is typically considered a hybrid protocol. It has characteristics of both link state and distance vector, and we'll look at those when we do the dynamic routing protocols tomorrow. So the link state, the Dijkstra algorithm, the database contains a full network topology, and the negative numbers can be used for cost in this thing. So what happens in the link state protocols, it is the state of the links, and the links are going to be the interfaces. When it gets the entire database, the router gets the entire database, it calculates its best routes to every network independently. The routers calculate them independently. Distance vector, hop count only, and there's no negative numbers here. And the little, hopefully not real great, but the illustration that we had earlier, it doesn't care about speed. All it cares about is the hop count. The routing table, information from the routing process is put into the database, and then the decision metric to build the routing table from the routing database goes on. And then the forwarding process we're going to request information from the route table to make the packet forwarding decision. The forwarding process, the route table has the information, goes into the forwarding information base, and the forwarding information base is actually the forwarding process here that sends the information from one. I think that we now come up to, the